Thank you very much for the invitation to speak, also for having me. My apologies that I cannot be there in person today. It was initially planned to do that, but hopefully we'll get this across in this virtual world as well. Unfortunately, we had to practice quite a bit during the corona, so hopefully this works. So I want to talk today a little bit, or Georg asked me to talk a little bit about our efforts in the Munich Quantum Valley, what we're doing there on quantum computing. As mentioned, I'm an HPC person, so I'm not a physicist. So I will not go into formulas and long physical explanations. I'll leave this to the physicist. I want to talk more a little bit about what these machines really look like, how we actually work with them, how we can integrate them into our workflows, and then what software we need to actually run them. So very much involved in building the software stack for the Munich Quantum Valley, and also how to do the integration with the HPC system. So that will be kind of the focus for today. But first of all, why are we doing this? What's all the fuss about quantum computing? Again, I'm not a physicist, so I'm not going to dive deep in, but basically there's a couple properties that we can exploit in quantum computers. We work on quantum mechanical principles, and they have the neat properties of being able to be superposition, which means every state can be there at one time. So there's multiple states at one time that can happen, that you can manipulate. So you can have parallelism with that. This is the easy way to express that. Physicists will probably be upset when I say it this way, but kind of in a basic idea. And that happens until you measure it. And then you also can do entanglements. You can form correlation between states. So if you change one state, the other change will stay with that. And hence you have kind of a communication. The until measured already gives it a little bit away. So you run something, you measure it, you get a result back. And you have to do this multiple times. The system is probabilistic. So you have so-called shots where the system will give you a result. You look at that at the end, and if you end up all the results together, that's what you get your final result, at least the most likely result that you have. And from that, you can form the computation. The basic unit is a qubit, which is basically the state. This is what you can superimpose and what you can entangle. Qubit is, as I said, more powerful than a bit because it can have these multiple states. But when you measure it, then it collapses and you get still a 0 or 1. So that's where the equivalency to the bit comes from. You program these systems with so-called quantum gates. A gate is an operation that you apply to a qubit. So that's, for me, mentally always exactly the opposite what you have in classic hardware. Here we have physical spaces that are these states, and then you apply lasers, microwaves to them. These are the gates, these are the operation. In the classic world, the transistors implement the gates, so there's some kind of static and you have something flowing through. But the principle is still, to some degree, the same, and people adopted the same terminology. And the idea is why we're doing this. Well, at the end, we hope to reach what's called quantum advantage. And there is that some algorithms, when you do quantum computing, require exponentially less steps than classic algorithms. That's at least the hope. At least that's how the theory goes. In practice, there's a lot of issues with that, a lot of challenges with that. And that's kind of where some of the work comes in that we're doing as part of the Munich Quantum Valley. Application domains, these are the classic domains that are always mentioned for that. It's not that quantum computing is like this general purpose computing. It's very much specialized to particular problems where we hope to have this quantum advantage, where it makes sense to invest all this effort into that. So actually, first of all, the simulation of quantum systems, because you can use a quantum computer which does these quantum operations to emulate quantum systems. There's work on optimization, which works fairly well. Machine learning is promising, and also some linear system work works well. But these are kind of the core areas that the people are focusing on right now to get some advantage out of this. Of course, as I said, there's some challenges in that. We currently still have a very small number of qubits, so we cannot make huge problems. Systems are still very noisy, so there's errors appearing up, and the state that you measure is not always the state that you would expect. That's something to mitigate. That's getting better over time, getting towards error correction, but it's going to be some while still. There's only very few algorithms. This comes back to the few application domains that are known. They're known to be working. Programming is still very specialized, so these quantum operations is not something that you can compare with any kind of high-level language like C, or even, I would say, even assembler is a high-level language against that. And at the end, you still have physics experiments. You're still trying to put this together. And that's actually exactly the challenges we have to deal with. It's a challenge we're trying to solve. And that's exactly the task of the Munich Quantum Valley. which is an initiative that was put together by now 3 years ago, or started 3 years ago, put together about 5 years ago, to bring together different technologies, bring together quantum technologies, bring together the HPC connection. And in contrast to many similar initiatives worldwide, not to focus on one particular way to do quantum computing, but on multiple ones, and with that to spread it. So looking at superconducting systems, ions, trapped ions, neutral atoms, and then of course the HPC connection. And as you can see, and just particularly saying this for you up in Franconia, it's called the Munich Quantum Valley, but there's a clear contribution already also from FAU in there. So FAU is a member of the consortium, of the MQV consortium. So it's not just Munich, but unfortunately the name stuck. So, but I think we may make this broader in the future. But it's the Bavarian Academy of Sciences, DLR, Fraunhofer, Max Planck, and then the 3 universities, the Friedrich-Alexander University, the Ludwig-Maximilians University, and the Technische University, who contribute to the overall project. The mission of the MQV is to build quantum computers, to develop and then also operate quantum computers that are competitive, also in close collaboration with industry. So this is supposed to make it to work with industry, to build with industry, but also make it available to industry, as well as multiple startups that are involved. And as I already mentioned, we're working with different modalities. So currently the most active ones are the neutral atoms, which are developed at the Max Planck Institute for Quantum Optics. The Walter Meissner Institute is here in Garching, is working on superconducting systems. And then there's the software stack, which is done jointly between TUM and the Leibniz Compute Center. And we're also working with startups in the area, which then take the technology and make it available. Planck QC, however you want to pronounce it, is commercializing the technology developed at the Max Planck Institute for neutral atoms. The Walter Meissner Institute just recently founded a company called Peak Quantum, which is going to work on commercializing the superconducting technology. And there's also been a foundation of a new company around the software stack, which is the Munich Quantum Software Company, which is going to help write customized software for an otherwise open stack. The MQV has grown over time. I want to go through all the numbers, but if you just look at the number of scientists that are involved, so we have 400 scientists involved in the project, large number of publications, large number of partners, several academic partners as well. Currently up to 7 ecosystem startups, and that's still growing. So it's really a large initiative that is not just your other research project, but it's really something that has been growing and building the community, and that's been actually really fascinating to be a part of. But now let's take a look at the quantum computer. So how will they really look like, right? If you trust industry, they look something like fancy like this, and you look at these glossy pictures, and people believe that they use large parts of compute floors to store these quantum computers. They have changed their mind in between, but this was some early pictures. And IBM also had something similar, which looks more like a design piece, right? But this is the idea how these things could look like at some point. If you look in reality, this is where the whole thing started. This is a quantum computer at the Max Planck Institute for quantum optics. So it's an optical table where you can build up your instrument. This is for the first time we started Quantum Valley, we got these visits and we got to see this, and we're like, how do you want to do this? How do you want to ever put this into a real compute facility? We told them you need 19-inch racks to kind of make this work, so we can put the slot this in the center. And then they said, well, we do have 19-inch racks, so that shouldn't be a problem. And so this is kind of the state where this whole thing started. They were lab experiments, basically. I'm kidding, of course, a little bit. This is the lab part. There's been a lot of work putting into commercialization, into packaging it the right way, of miniaturizing them, making it available. And currently, several of these systems are already at the LRZ, at the Leibniz Supercomputing Center. So you have here a superconducting system, an example of that. You see here the cryostat. This is the cold piece with the control rack on the left side. This is an ion trap system from a company called AQT, Alpine Quantum Computing. They're already putting this fully into racks. There's an optic system and an ion trap in there, so a vacuum chamber with ions in there. So they're turning more into commodity systems that we can put these commodity structured system that we can mix with existing HPC hardware. How does such a system work? This is a schematic that I stole from someone that kind of shows really nicely, though, how a superconducting system looks like. You have this fridge here. This is this long pot basically that's hanging here, where in the bottom you have the quantum processor installed, and everything in between. Typically, pictures you always see these beautiful golden chandeliers. There's nothing else but cables that try to get the signals from room temperature without running into any kind of electrical problems down to a cryo area where you're in the millikelvin range, to where you can kind of operate these superconducting chips. That is connected with a refrigeration unit on the outside, which helps you get this down to these temperatures. The whole thing is held in vacuum, again, but to better reach these temperatures. And then you have control electronics on the side that somehow connect to your data center where you send in this case, microwaves, and that one you can connect and then control the individual chips. So you send these gates in via microwaves, and with that you can control the chip down here. And these chips look something like this. So this on the right side is a picture from IQM. This is the system we have installed here as well. So again, you see this beautiful chandelier. This is all just connectors. The chip sits somewhere down here in the bottom where it's connected to. Here's a different system from a D-Wave. It's not quite the same type of quantum computer, but it's the same principle of refrigeration. You have the chip here in the very bottom of this arm, and then you cool the whole thing down. And you have multiple temperature zones until you really reach up to that. So the computers are manufactured onto a chip in this case, in the superconducting areas. You control them from the outside. There's no internal control architecture. It's not that like what you have in classic systems that one transistor influences another transistor. It goes out, there's a control outside, and you send the next signal in. And as I said, this is also noisy, and that's also hence referred to as noisy intermediate scale quantum computing. So not quite large scale yet. Noisy because we see a lot of errors still, which should be referred to as the NISQ systems that we have currently, which are already starting to be helpful though, despite being noisy and error driven. And if you look now at other modalities like the neutral atoms, the physics is 100% different. Here you have atoms you throw on a glass plate, and then you take pictures off with a camera and you analyze the picture. But from a computer science point of view, it's actually pretty much the same. You have some physics setup, you have some control unit. In this case, you control lasers. In the other one, you control microwaves. This comes from a control unit so that you can very finely tune these different mechanisms. That gets controlled from a system, and that gets connected to an HPC system on the other side, right? And so this connection to the control unit is also our interface to the system, how to shape these pulses, that then control either a laser or a microwave. Of course, there are different pulses for different systems, but at the end, that's hidden in the control unit. So for us, the interesting part is that connection. And so again, it's a different control, different qubits, but very similar from the control side. And so this one is also, I want to make very clear, we don't believe that quantum computers will basically take over the world and be the only thing that you have. They're very specialized for very particular things. So what sometimes you read is that the quantum computers will replace HPC. I rather believe that quantum computers will be accelerators, and we will talk about quantum accelerators. They will help speed up HPC system, HPC codes, and hence are similar as GPUs, FPGAs, or large-scale accelerators like Cerebras systems are also part of HPC. And that's kind of how we're also trying to operate them and build the infrastructure around it. And so we're trying to really bring quantum computing into the fold of high-performance computing as part of the Munich Quantum Valley, and with that add to the compute capabilities that we have, that we need in the supercomputing portfolio. We all know we're ending the end of Moore's law, we're already past long the end of the NAR scaling, and so we're looking for new specialization architectures. And this is kind of an extreme in this area of a very specialized architecture, but which has very high potential to solve that class, that potentially very important class, very fast. And so we're trying to get the quantum computers as an accelerator into HPC. And that is said important because we cannot see quantum computing as standalone systems. In particular, its growing scales, right? So we already talked about the control systems. Those will scale up too. At the end, you need to control every single qubit in there. So you have thousands of qubits. You also need thousands for away control. You need to do some data staging and post-processing. This is not huge, because data is not that big in quantum systems, but nevertheless, they need to be done through classic systems. You need to target very specific workloads and very specific kernel. Those will be offload kernels. Also, that makes sense to combine with some classic workloads in tight interaction. The so-called variational algorithm, which have a loop on the classic side, generate small kernels and push them off, and then have a tight interaction. So that's one of the very, very common ways to interact. Again, needs to be able to combine the classic side with the quantum side. And this is kind of the other way around too. Compiling quantum circuits and making quantum circuits run well, creating these pulses, optimizing this, are complex algorithms by themselves. And so we're actually trying to use HPC by itself to enhance these systems. So it's not that just quantum can help HPC grow, but HPC can also provide the power to run the quantum system well, particularly as we scale. And so both interactions, I think, are very important. And so we're seeing them exclusively as accelerators for HPC workloads, for fine-grained kernels within larger applications, as workflows that then can be targeted off, very similar to accelerators. And you'll see at the end, the way when we start talking about programming then, we're trying to actually also do a very similar approach in programming them. And as a consequence, we really want to see them as a single system. So we have the same question of tooling, right? So how do we extract application components that are relevant? That is easier if it's a single system. We need to basically, as of access for the HPC community should be easy. They're used to this kind of single system model. That's kind of what we're trying to emulate. We require an integration to a single programming environment. They should not be distinguished one. If you want to couple them, they should be coupled already on the programming side. User access management sounds trivial, but that is important to do to get kind of a unified user experience. So you don't have independent queues like what we have. Sometimes you do something here, you ship it to the other side of the world. You have to wait until they're done. This is not a nice user experience. That works much better if you have this centrally in one place. And then also we're trying to get a better hardware integration to make these latencies between the two systems small. And the way we do this is also kind of evolving over time. So this is kind of where we all started. You have an HPC system with a high-speed interconnect that has its own front-end system with its own scheduler, its own login nodes. You have a QC system standing somewhere else, which has its own front-end node, and there's a facility backbone in between. And so whenever you want to send something, you ship this out, potentially even over the internet, you come in here, you have a new queue, you have to wait, you get the answer from the quantum system, and you ship it back. So it's kind of a very loose coupling, which is relatively easy to do. It's already useful for certain things, but of course you're missing the tight interaction. You potentially have a long latency because of the network connection and the double queuing. But we then went as a next thing, we actually started to introduce not just a front end, but we had a quantum access node. This is how our current systems actually run at LRZ, where you have a quantum access node connected on a high-speed network to the system over a control network, then goes to the QC system. So you don't have to go through the backbone anymore. You can go through an intermediate scheduler. You can have easier access to the quantum system, and then we'll operate in that. And ultimately, where we want to get to, and this is kind of our first experimental setups are going in this direction, that you actually drive the control system directly from within the HPC system. So you even get rid of the access node. Each HPC node will become an access node to go to the control system, and that is the minimum latency that we can get then. There's a couple of technical hurdles, of course, to overcome with this one, but this is our goal where we want to end up ultimately. And to make this work, of course, you can imagine now, this means you really have to put them together. And this is kind of, this sounds trivial, but actually ended up being quite a something learning experience for us, because there are a completely different system. They use different water temperatures. They need compressors. They have suddenly nitrogen handling involved. They have a different form factor. They have different vibration sensitivity. They have different noise sensitivities. And so learning all of that was, it took us a while and get it right. But we have now been able to install one system already on a real machine floor. This is part of the LSE Compute Center. And where you see the purple dot, we're actually currently building up the new system, the second quantum system, the new EuroQ access system. And this is a picture of the Q access system, the first one that we installed. So you see here, again, this part of the cryostat, the control electronics with all the microwave cables that then go out and go on top of the cryostat. And back here, some completely unrelated HPC systems, which then there's some other control systems behind this cabinet here where we can control and we can work together with. But this is within a regular compute environment now. This was built by IQM as the first German quantum computing demonstrator, was inaugurated last June, so about a year ago now, and is currently still in friendly user phase. We're trying to transition to a more organized standard operation. So in the next couple of weeks, months, we'll have the system as standard operations available to users. And then also as part of the system, the team at LSE also managed to do a real run that's connected, in this case, SuperMOOC NG, our current flagship, together with the quantum computer for a real coupled simulation. This was the excited state at the end of the experiment, where we believe it was the first one that we actually run on-premise systems together and had a really hybrid application running for co-located HPC and quantum system. So it's kind of a milestone that we can demonstrate that this will actually work. The next step for us on the system side, there will be 2 more systems coming in the near future. So I said the first one is currently being installed. I was just over there looking at the construction side. It's currently open, so this beautiful chandelier is currently showing and cables are being put in. That will be available in a couple of months, still in 2025, and next year in 2026, we'll have a 150 qubit system standing at the place where you before saw the older QXS system, with this idea of being even tighter HPCQC integration, working closely with IQM to make that work. As far as other systems, just a quick overview. We currently have also an ion trap system, was the other picture that you saw with 20 qubits. There's multiple superconducting qubits in the lab. These are the new superconducting qubits systems coming in. The next one I said the final one next year. And we're currently also building up a neutral atom system, which is about 1,000 qubits. You're going to ask them, why is this 1,000? Why is this 150? They also have different time spans. They have different properties. So the compute capability is not just measured in qubits. So the capability will probably be relatively similar between the two, even though there's an order of magnitude difference in qubits here. So, but coming back to the challenges of bringing these in, so it was quite difficult to figure out what we need to do, how to understand. The vendors didn't know that, we didn't know that, so we needed to find out the right way to bring the system into the HPC center. And so one of the first things we asked ourselves is, what is the environment actually like, and what in the environment affects the operations in a quantum system? As I said, they come from a lab, they come from very controlled environments, they come from environments that do nothing else but cryostat experiments. There's no HPC system next to that. So what is really the influence between the two parts? And so what we started to do is so-called telemetry. Let me just get rid of this another such noise here. Hopefully that will help. So we did some what we call telemetry. So we're trying to, like similar what we do for HPC system, try to measure everything of the system and of the environment of the system, so we can afterwards have a correlation, kind of figure out where things work well. So we go towards data analytics and try to understand what influenced the systems and kind of what was bad for the system, and how can we mitigate for that with right shielding or other operations. We actually use for that the same system we use in the data center itself, the data center database that was developed at LSE actually for energy monitoring, and is used in production there. And we expanded this to also then include sensors in the quantum lab, so we can kind of measure things from within the system, but also environmental ones. And so we're currently tracking about 1,100 sensors, all kind of stuff that we could think about, from simple things like temperature, air pressure, to humidity, movement, doors, how many people are currently in there, how much is spoken around the system, any electromagnetic waves, so anything we could think about to kind of figure out what are these systems really sensitive to and what do we really need to work against. We're collecting this data, we started the analysis on that, and so this is going to be a very worthwhile and very interesting data source for us. We're putting this whole thing through Grafana at the moment to kind of look at this. There's an example up here on temperatures, and then also we're doing more and more of machine learning, where we take these parameters and try to correlate them with what error rates that we see in the system or other behavior we see in the system. And this concerns to some funny things. So this is one of those sensors. that measures electromagnetic waves. And you can see a very regular pattern here. Down there, you see the time, and you see every 10 minutes a spike happening, and suddenly it turned into a 20-minute spike. We were first of all asking ourselves, well, what is this? What's going on here? It turned out this exactly matches our subway schedule in Garching. The Garching subway is about 100 meters away, but it was enough to still create enough of an electromagnetic wave. You can kind of see it was a Saturday experiment. At quarter past 8, we turn into a 20-minute schedule. So this is kind of here the 20-minute where we turn into the schedule in this part. So even things like this can go all the way to the quantum labs, can potentially affect things. And this is exactly what we like to catch with this kind of experiments. And this is kind of a fun thing now to see. Now, of course, once you know this, you could actually now, we're starting to talk to the subway providers. Can we get actually a sensor for the subway and not just measure the electromagnetic waves, so we can actually understand if there's something happening on the system. Okay, so this was mostly hardware now, but I promised in the beginning I will talk also about the software and how to make this work. Now we have these systems standing there. We have them connected to the HPC, but how do you really now program and operate them? And there, the role of software is really to connect domain experts to the various quantum devices. It's very similar to what we have in classic stacks. The domain experts are kind of the new thing actually in quantum, because in quantum computing, typically we initially target towards physicists that use them as the lab experiments. But now the idea is really to make this available to domain experts in a way that they can use it and easily use it. And if you do this traditionally, you end up with something like this, where for every domain, you had a different path, a different stack for every different modality, and that's obviously no longer sustainable. So what we're trying to shoot for is look something like this, the so-called Munich Quantum Software Stack, where we're introducing a large-scale AI-IR. We're working here with industry partners through the QI Alliance, which has several other industry partners and their lab partners in there, as well as MLIR, which are all part of the LLVM compiler infrastructures. We're using classic compiler infrastructure to do, for one, the compilation of quantum circuits, but then also to start adjusting to the point that we can use classic and quantum in one source code, in one intermediate representation, so we can actually keep them together and semantically keep them connected. And this allows us to then connect the software developers to the hardware providers, provide support for the different user communities, and then also integrate this whole thing with the HPC systems. And so with that, we'll be building this Munich Quantum Software Stack. The goal was from the beginning to support a wide range of quantum computing modalities. That was always the point of the Munich Quantum Valley, just to not shoot for one, but shoot for multiples. Wide range of programming models, from the standard existing Python models, so most of the quantum systems are developed with some kind of Python scripting, all the way to HPC-like approaches, and I'll show an example of that towards the end of the presentation. We want to, of course, support the integration of quantum computing into HPC. As I said, as an accelerator, that requires some hybrid programming, high-priority program abstractions, some new programming models, some languages for that. And then that's probably the biggest challenge. We want to make sure that these resources are utilized efficiently. Both of them are very expensive. Both the HPC system and the quantum systems are very expensive, and so we cannot leave them unutilized, right? And so we would like to make sure that when one is not used, we find another use for that. We work with dynamic resources potentially. We can schedule them ahead of time. We understand really how the usage is, so we can interleave potentially operations. This is a classic scheduling problem, but that's going to be key to make the idea of quantum computing work well. And then last but not least, we also want to support easy management. I mean, this is supposed to also work for not just the users, but the administrators. How can you make this work as one system? How can you manage it? How can you have the proper portal? And with that, hopefully then support both internal and external users, as well as administrators, and also multiple installations. So this is not just running one quantum system. The stack will actually run multiple systems and can dynamically choose which system it wants to go for based on the needs of the quantum circuit, the needs of the user, and also the access rights, of course, to the particular systems. How does this look like now? This is the part of the compilation. So you go from some kind of somewhat specified high-level code to various devices. This is a classic compilation process. We use a path-based management here, similar what we would do when we use LLVM on a classic system. There will be some device-agnostic compilation passes first, which optimize the system first completely without looking at the device, and just this can be mostly done offline, actually. At some point, you need to choose a device. So you make a pick which one device you want, which class of devices you want. Then you would get to another set of passes which do compilation specifically for that system, that take this generic description and lower it to the particular instructions available on the devices, that optimize for the property of the devices as well. And with that, of course, we need some mechanism to figure out which device is available and what the status is. So there's some live feedback at this point necessary, which automatically mean everything on the right side here has to be at runtime, which then, of course, puts pressure on what kind of latencies we have, what kind of speed we can do this with, and so on. But basically, from here on, you're guaranteed to be at runtime part for your software stack. To then optimize the compilation passes, you also need to figure out what the system is currently looking like. So we have seen qubits evolve over time, getting better, getting worse. We've seen some qubits having good and bad days. And so knowing about this and knowing how they're connected allows us to kind of optimize a computation for a particular device, kind of a topology mapping that you do it towards the very end of this compilation process. And for that, we need live feedback again from the system, so to understand that. And then at the end, once you have all that, you can submit the job. And a job submission at the end means a set of pulses is being shot at either via lasers or microwaves onto the device that holds the qubits. So this comes now the control infrastructure, which then turns this job, this gate description or pulse description, to actual physical pulses that are being sent to the systems. And then also, these systems don't start off fresh. Typically, you have to calibrate them. So you have to kind of run some test runs to make sure that the device actually is properly stabilized. The pulses are the correct one matching. It matches the environment also that you're in. Even if you just change it slightly, that may knock the calibration off. So this is also something you do on a regular basis. And so all of these kind of features, this interaction between the compilation process and the device. So job submissions, finding out which status is, finding the constraints, doing the calibration, is kind of our backend interface into the device world. We're calling this QDMI, the Quantum Device Management Interface. It's an open source software component that we can download and can play with. Put the link here also on the top left if you're interested in that. So this is kind of our idea to help standardize this last mile to the devices, and with that make systems a little bit more interchangeable. This one you can submit jobs into the device, you can get information back in form of results, and you can get information back in the form of these feedback mechanisms from the device, which we dubbed FOMACs, figure of merit and constraints, which show us what the devices can do, how they're doing right now, give us the health status, get us the availability, and that again can then influence the device-specific compilation paths. And then to make this work, we added a whole bunch of backend systems now for the different systems that we have at LRZ, for the systems we have at the partners like WNI and Max Planck. We're adding things for the different startups. We're adding backends for simulators, and there can be, of course, a whole bunch of different backends as well. Those are then device specific, those are technology specific, but they can then plug in and then with that enhance the QDMI interface. And so this gives you an implementation that looks like this, where you have a user-facing interface where you have one single way to interact with that, and a set of backends which are plugins based on the modality that can be vendor provided, that can be self-written, but these ones would then actually control the control system, and this part then would allow us to act and interact with arbitrary systems. And as I said, this QDMI interface is an open interface. It's actually based on C, so we explicitly went away from Python to be faster, to be more interactive, to really be a low-level interface. A lot of the stuff in there was inspired on one hand by MPI, on the other hand by things like OpenCL that allows also this kind of widget handoff. Then there's this whole thing is versioned backwards compatible. So it will be the idea is to write this up in a similar way as MPI and also maintain it in a similar way as MPI. The intended connection here is that on one hand, you have the vendors as the providers. So this is the right side of this QDMI interface. And then you have the quantum software stack itself, that then interfaces that uses QDMI to talk to the system at the end of the compilation cycle. Everything is based on plugins, so we can add new systems, new support, new capabilities by adding new plugins, new backends into that. There can also be multiple plugins active at one time. If you have multiple devices, they can be there. Things can be forwarded to remote sites. So this is a relatively flexible concept. And then the API itself, to get information back, is a key value type store where you can then ask for properties back from the devices in a device-independent manner, which then can run into the Formex libraries and then can run into the compilation process again. We're trying to do QDMI not just as a research software. This is really intended as a support for the community, as a support for running large-scale systems. So there is a continuous integration, continuous deployment setup being developed around it. We're working with several companies who are picking up on this. And so we're hoping really to create a community around that to make this work and to have one interface that then everybody can connect to. So we're definitely looking for external contributors. If somebody's interested in that, please join us, send us email, contact us, look at the software. We're definitely open for feedback here. So if you look now at that whole stack, so this is the backend part. We have the telemetry system on top of here, which then connects with the user management, which then connects also to the system administrators. This is the software I mentioned before, where we're building on the DCDB, which then also has an interface to the quantum job scheduler, which collects timestamps, analyzes the data that comes out of the database, and at the end then also allows us to do proper data labeling and create models that allow us to better understand what's going on in the system. So also that part is a full infrastructure which is put up here. The other part of the MQS architecture is the compiler framework. This is what I showed before with these different passes, both the agnostic ones and the system-specific ones. So these again then have plugins. Then these can then read these figure of merits, which are returned by the QDMI interface. So this is the compilation part. Here, the idea is also to keep that framework open source and then have different technologies plug in with either open or closed plugins on that side. And this MQS part is growing relatively rapidly. So this is not just a single piece of software. This is a base framework with a lot of plugins. And as part of the Munich Quantum Software Stack efforts, as part of the MQV research efforts, there's a whole bunch of different technologies being added to that on the back end, on the middle end, on the system side, but also on the front end side. And you see here the respective contacts at the respective universities or research institutes who are participating and working with us on that to grow the software stack. So we have this component catalog, which is still growing, which we're trying to also grow with new technologies, with new compilation paths to kind of grow the ecosystem there. After this, in the middle is also a scheduler. There's already mentioned that the scheduling is going to become critical to make sure that the quantum computer is always used and the HPC system is always used. But then the next and the last step then is Python data question now, and how can we program that? So there's another challenge in the HPC integration next to the hardware part and the scheduling part, which I already mentioned. So how do you do this hybrid programming? How can you program for an HPC system and a quantum system at the same time? And so one of the first experiments that we did with that, and it's not necessarily how it will shape up at the end, but we hope this at least gives them an impulse. We developed something called QPI, the Quantum Programming Interface. And the idea how this works is, if you work with a standard HPC system, you would log in this case to LSE, to a login node. You would run a Slurm or some kind of other you preferred resource manager, which would then spawn your job to the compute nodes using the Slurm daemon, would run the application on that, and then you would, of course, then have an MPI program to connect them together. If you have local accelerators, you have something like CUDA potentially involved to run your NVIDIA GPUs, or your other favorite dialect to run your other favorite GPU. And then you would have another library called QPI, which is also an offload library. So similar than you send kernels to CUDA, you could send sandals to QPI as well. The big difference now, of course, is unfortunately we don't have a quantum computer per node, so or per core even. So we actually would like this. We need to have a different granularity. So what's actually happened here is the QPI would then contact a quantum daemon, would then talk to the backend architecture, which then kicks off the compilation process, which kicks off the machine selection, which creates the final pulse sequence, which submits it over QDMI, submits it to the quantum system, and then gets back for that. And now you can also see why the scheduling is so important, because potentially we can have many more of these systems here compared to the quantum backends. So that could overwhelm the quantum backend, create idle times here. On the other hand, if the compilation process is very difficult, this could also create idle times here, because we can get stuff quick enough to that. So finding the right balance between these two systems is critical. But you can make this work and look something like this. So this is an example of a QPI code. It has a similar abstraction than what we know for Qiskit. So this is the standard system used by mostly, which is from IBM and very much targeted towards superconducting systems, but it's Python based. It's relatively slow. We wanted to make this more architecture neutral or vendor neutral, but we still have the same gate type of abstraction. But we really wanted to have the support for the legacy HPC application concepts to make the learning process relatively low. So it's also a C-based API, and it uses the typical accelerator concept. And you can see this here in the example. You're starting to design a circuit. So this is the set of gates, the set of operations you want to do in the quantum. You add two of these gates. This is an Hardeman gate and a CX gate. At the end, when you run these two gates, you want to measure that, and that's the end of the circuit. So that's the snippet that you would like to run on a quantum computer. That one gets then executed. You have a process that's similar to an MPI non-blocking communication. You send something off, you get a status back, you wait for this to complete, and after you complete, you can actually read the status. That's these multiple shots that are being taken on the system. You can read this out, you can get the histogram for that, and you can print out the result. There's, of course, a very, very simple circuit. You could do a much more complicated circuits in there. But this now allows you to build circuits, execute them, wait for the results, and then potentially come into an iterative process to make this work. So that's kind of the idea of QPI, is one of the very low-level ways to do that. And of course, we have known how to do these offload things in HPC. And now, of course, the immediate question came, can we use one of these existing offloads instead of coming to something new? So we actually tried this as well. And we created a quantum computing capable OpenMP. So there is, this was, to be honest, kind of duct taped together. It was an experiment, but it at the end worked fairly well. So we have a Pragma OMP target. The target accelerator is, in this case, the quantum computer. We do a loop after that. So that's kind of a new experimental part here. And you would have now a loop in there. So you wouldn't run this in parallel, right? This is the shot loop. This is the stuff that you send in, but this kind of gives you control of how many shots you want, and then you have an aggregation of the results down here. You again build the gates individually, you create a schedule, and then you kind of execute them down here. You get a result back. This is one result, it's typically one number. You build up your result index yourself with that. So this is code that kind of gets offloaded close to the QPU, and then the shots will be taken from there, and at the end you can print that. So these are kind of first ideas how we can really combine existing software stacks and the quantum software stacks into one piece. And this kind of completes the software stack. I know this is kind of an overwhelming picture, but it gives the idea of coming from a front end with the HPC access, with the HPC access libraries, over the proper scheduler, which is typically a separate scheduler from the system scheduler, into the compiler with its plugins, through the backend interface, into one of the actual drivers of the system, which then creates the pulses and actually runs the system, combined with the management interface to get the telemetry done. The idea is to make this will be all open source, except for some plugins that vendor want to keep for themselves, but the whole infrastructure will be open source. The QDMI is already open source. We're close to open sourcing the compiler framework and some of the front-end interfaces here. And then hopefully everything will fall together and create this one large open system. So looking forward, what's next for the MQSS? So we're working, been working on this now for 3 years. This will be still the work for MQV1, which runs for another 1.5 years. And after that, we're looking into MQV2. And there's kind of 3 goals what we want to do that. For one, if we want to really do this operation of quantum systems, we need to stabilize the MQSS. This is not the sexy work. This is engineering work. It needs to continue to grow. We need to support better support for integration, for testing, for deployment, document user interface, and also transfer the whole stack into operation so that the users at LSE can actually use that as the final users. So this will be something kind of a non-research effort in MQV2, but it's essential to build the ecosystem and drive the software stack forward and make it usable. The second thing is we will evolve MQSS, add backend systems, add better optimization, add more plugins, basically extend that component catalog that you have seen, add some more abstraction into that as well. And of course, also start supporting some of those components, but more in a kind of a researchy setting. Once they're really successful, they transfer over to the stabilization. And then the last thing is also, there's also, of course, some basic research still needed. We're looking into what we call the revolutionary parts of the MQSS. This is done to do with fault tolerance and error mitigation. So how can we go beyond the NISQ area, can find a way to correct errors that appear or mitigate error as they appear. This is still very much basic research work that has a potential of transforming large parts of the MQSS, but also that we see as a moving target, so go from revolution into evolving MQSS back into the stabilization. The core team is shown here. So the whole effort is run by Robert Wille and myself. We have Laura Schulz, who used to work at LSE and has driven a lot of the ideas as well, and is still connected to us as well. And we have Lukas Burkholzer and Jorge Echeverria, who are our technical leads and who drive the actual design and the testing, deployment, and also the extension strategy forward together with us. If you're interested in that, more information, please feel free to contact us. This email reaches all of us, and we can then certainly have an interaction, see what we can do. But then, of course, this is also not work by just 5 people. This is really a big thank you for all of our teams. We have large teams that are behind us at the universities, the CAPS team and the CDA team, and then also the larger team at LSE, the quantum team. This is really a big effort to move this forward, to get towards this new version of the software stack, and with that, hopefully at the end, enable quantum acceleration for these hybrid HPCQC workflows for the NISQ areas, but also beyond once we get into the error-corrected areas. I hope this gave a good overview of what we're doing. I know this was perhaps sometimes a little bit of a high-level overflow, but I hope it was interesting, and I'm happy to take questions and also go deeper if people are interested. Thank you very much.
Thanks a lot, Martin. That was a very enlightening talk. The discussion is open. Please raise your hand if you want to speak up. There's also some questions in the chat already, and I'll just start reading them. The first one, how does the current state of quantum computing and quantum encryption in Europe compare to other regions of the world, such as China and the US?
So I'll be honest, I cannot say much on quantum encryption. That's not my area. I would leave this to other experts. For the quantum computing part, it's actually a mixed thing. So of course, some of the large companies in the US are further ahead. When you read the news from Microsoft, from Google, and so on, we've done huge efforts in that direction. Quantum companies are also perhaps a little bit more aggressive in the US, but we're catching up really quickly. Companies like IQM, like PlanQC are definitely competitive and are seen as competitive in the international marketplace. As part of software is concerned, we're actually, and not to be too pat on our own shoulders, we're actually leading. Some of these HPCQC ideas really came out of these efforts here, and people are looking to us. That's also why we have so much success right now with the QDMI interface, and people are willing to take this on. So we actually have we are among the worldwide leading efforts in the quantum software. As far as China is concerned, there's huge efforts there as well, as far as we know, but they're not telling us much, right? So we don't know exactly where they stand, but probably on purpose. But there's definitely a lot of money flowing into quantum computing in China as well. So there's huge efforts going as well. And some of the publications we have seen are certainly also show a very strong research effort in that area. So it is a race between the continents, and I think Europe is a pretty good standing right now.
Hello, very nice talk. I'm amazed. I'm not doing currently any research on quantum computing yet, but we are compilers for LoopNest to parallel computing devices, and there the biggest challenge is how to parallelize typically sequentially written software. And I wonder, is there an analogy here for quantum computers? If I understood well, your intermediate is must be also something naturally parallel like that. These are these quantum circuit descriptions, right? And the back end would be mapping the quantum circuit to some also like instructions of von Neumann to instruction sequences of controlled sequences of instructions on your quantum device. Is that correct, first of all?
So principally, yes. So it's basically trying to break this down to the individual gauge, which then turn into, you could see them as instructions, which turn then into the pulses, which are kind of low level, like microcode instructions, if you want to compare it to that. That's certainly right. The parallelism is certainly there. You have a large number of qubits potentially, and you want to make sure you map this correctly. There's a topology problem similar we have on the classic HPC as well. Which two qubits can do better together, and how do we reduce communication between them? That's certainly there. And then the other comparison, I think you're absolutely right. Parallelizing the existing software in this compiler stack, we know that these algorithms are very difficult and very high complexity, and so doing this is tricky, and that's something we're still attacking. And we learn a lot, or we take a lot from the existing compiler community as well, because some of these problems are very similar at the end in the transformation. But we need to, so right now, this was not a concern because you deal with 5-6 qubits. Even if the algorithm is exponential, nobody will care. People have written this in Python on their laptops. And so there was not really a need. But now that we go to hundreds and thousands of qubits and we have HPC systems available, we're actually focusing a lot on making the software stack itself parallel and efficient. And we run into the same problems that the community has been running for a long time, obviously.
Yeah, thank you. So if I understood correctly, so this QPI is helping if you know already a quantum algorithm and how to manage this getting it on a machine. It does not solve the problem. How do I get from dirty code, which is completely sequential, solving standard arithmetic or whatever problems like matrix vector type of workload as you accelerate on HPC, how to get this into quantum circuits to exploit the beautiness and this entanglement of at all advantages of a quantum computer. That's unsolved still, or also your tools support this?
No, you're absolutely
No.
right. I mean, if you look at this, this is the quantum circuit, and this is a totally different way of programming. And I've seen no even attempt right now to take a standard code with the abstraction that we're familiar with and transform this automatically into quantum code. This is a totally different world, and to be honest, I still have real troubles wrapping my head around how you do even design quantum algorithms. They're really different. So you need to know your quantum algorithm. There's some algorithm zoos being developed right now, so you can pick and choose from. I think a lot will run over libraries at the end. So if you detect a pattern, you know a certain library matches that pattern. That one I can see automated, not the actual circuit generation. I would be surprised if we get there anytime soon.
I heard also about a company Classic with Q at the end, Israel company, but I have not checked whether they are able to solve this problem. I believe they cannot. Yeah.
No, also the Classic, I think, does a lot of workflows. And so they're helping stitch things together. If you have individual pieces, right? They're helping a large circuit, take large circuits apart is something that people do and schedule them. But you always start with a circuit and an algorithm.
That helps me a lot in understanding. Thank you very much.
Sure.
All right, there's another question in the chat. Where can we find the QPI software? I know that the Munich Quantum Toolkit is on GitHub. Is that where the whole development is done?
No, not quite. So right now, be honest, the QPI is not available yet. We're kind of polishing that and getting that out sometime soon. What's available is the QDMI in the back part. And several of these components are starting to become public and available. And the Munich Quantum Toolkit is a collection of these components. So these are closely when they have been developed independently. We are pulling this into the software stack now. This is work in Robert Willis' group. So these are individual components that live within the larger stack, and QPI will also live in the larger stack. So it's just, you see here's another component that will be eventually released and be made available. If you're interested in that, looking at that earlier, feel free to contact us and we can give early access to that. I expect the open source stuff to be in the next couple of months.
Yeah, so I wondered of the kind of GPU hardware you installed, what of this has fast enough networking for quantum error correction? So what's the latency time for feedback? I mean, that's essentially, I don't know. I think that's essential to kind of know in what respect this can be also scale.
That's absolutely right. So the ion traps and the neutral atom systems have relatively long coherence time and also long gate times. So there you can actually bring this back into a tightly connected HPC system and run an error correction relatively easily. We are not quite there yet because there's still a lot of stuff to be resolved, or just from the pure latency times. This should be possible, and we're actually looking into this together with the AQT if we can do some research on that. On the superconducting side, you have much shorter times and also much shorter gate times. So this, as soon as you come out of the fridge, it will be really difficult to do full error correction. We hope to get some error mitigation, some error correction after the fact, but not fault tolerant as we're running. If you want to do that, you probably have to get closer, and people are also looking into that, of taking some of the electronics, some of the cryoelectronics inside. But this will have to live below the stack then, because then you're really inside the QPU basically, or inside the fridge, very close to the QPU. But for the superconducting, we'll have to use some techniques like this.
One last question from the chat. Is there a strategic plan to collaborate with the EU's AI Factory and Data Space Initiative?
Wow, that's a good question at the end. To be honest, the AI factories are relatively new in that sense. There hasn't been made an official plan yet. I would imagine sooner or later that would make a lot of sense. And there's some places also where you have multiple systems, where you have AI and quantum systems in that sense co-located. That would be quite interesting. Right now, the current first step will be to have all the different Euro HPC quantum systems to work together and kind of also connect to the HPC systems. But I would imagine sooner or later we'll do the AI systems as well. There has been quite interesting applications being developed or starting to be developed, which work in this triangle between quantum AI and HPC, where you have the base model in quantum, you do machine learning based on the model in the AI part, and you use this as surrogate models in the HPC. That will require power from all three sides, and sooner or later we'll exploit that. But I think the AI factors are just a little bit too new, and also here in quantum we have enough to do to connect just the HPC quantum systems together. But sooner or later, probably more, rather sooner or later, we'll go there as well, I'm pretty sure.